So good afternoon, everyone. So I'll be talking about the topological Casimir effect in U1 gauge theory. So don't leave yet and don't freak out. I'll explain the title. So Casimir effect. So let's imagine we place two neutral and massless, perfectly conducting metal plates in vacuum. Normally in classical ENM, we expect nothing to happen. Right? This is very intuitive. Nothing should happen. But if we consider the same physical setup in QED, quantum electrodynamics, we expect an attractive force between two plates. And that's called the Casimir effect. So let's get a more intuitive picture into this very elusive effect. It seems that there is a force from nothing. How do we make sense of it? So essentially in the quantum vacuum, it's more or less a violent, stormy sea of particles constantly creating and annihilating each other. So what happens is that when we place the two plates in the middle here, it quantizes the space in between, and the photons, these virtual photons that can come out of the vacuum, can only take on discrete energy levels because it's a quantum system. But outside the plates, there's no restriction from the plates. So the photons, the virtual photons that are forming outside can take on any frequency. So effectively, we can have more photons, virtual photons for that matter, forming outside the plates than the virtual photons forming inside the plates. So that creates a pressure difference between outside and inside the plates, and effectively creates an attractive force. So usually this Casimir effect is calculated using vacuum energy, and believe it or not, the vacuum actually has some energy. And it's analogous to our simple harmonic oscillator in quantum. So in the simple harmonic quantum system, when we have a ground state, the ground state energy is non-zero, and it's given by 1/2 omega h bar. And it's very similar to the vacuum energy is in fact very similar to this guy. So for the following derivation, I will set all constants to 1. This is a standard thing. And let's keep in mind the geometry of the system that we're considering. So we have L1 and L2 here being the x and y dimensions of the box. Of course, I'm using a box, but it is very similar to using two plates, and essentially the same. But the thing to keep in mind is that L3 is much less than L1 and L2. So I'm not going to show much math here, but essentially I'm going to use a toy system that's called the scalar field. It's not a physical field, but it's very useful for a lot of the quantum field theory calculations. So if we calculate the Casimir energy, which is defined to be the energy difference between the vacuum energy inside the box and the vacuum energy outside the box, we take the energy difference, and then we get this long string of things. But the point is that we can extract the force out of it. Essentially, the force, just by taking a simple derivative, can be shown to be proportional, inversely proportional to the plate separation distance, and it has a negative sign, means it's an attraction. So similar calculation can also be done for electromagnetic field, which in this case would be a physical field to calculate. And that calculation can be done in Minkowski space. So Minkowski space is the usual space and time extend to infinity. And that can also be done at finite temperature. So instead of the previous calculation, we just now add the thermal correction to this force. And it's commonly accepted that the force for the electromagnetic field is just twice this guy. And because photons have two polarizations, everyone knows that. It turns out that it's okay for this one, for this Minkowski space, but in general, this is not quite true. And for the following, I will consider a U1 gauge theory on 4 torus. So let's explain some U1 gauge theory. We don't need to know the full extent of U1 gauge theory, but we do need to know what is the gauge field. So if we call from classical ENM, we have something called the vector potential for magnetic field and electric potential.